All right. Good afternoon, everyone. Welcome to HRAI's next webinar. My name is Matthew Bradford, your host. You can see it right there. Anyways, thank you so much for joining us. We got actually a lot of people here, which is fantastic to see. I know it's a busy season for you guys, but we have a really interesting webinar for you. A bit of a switcheroo last minute, though. You're used to seeing Phil present on this, but this time we have his colleague, Jonathan Byrne. You're in good hands. He's got a lot of information to share. The topic being getting technical with compressors, controls, and wiring for reciprocating compressors. He's going to be taking you through that. And at the end, if you have any questions, we're going to give about 10-15 minutes for that. If you'd like to ask a question, Phil is also in the audience. I'm going to turn on his audio during that time. He can help out. But if you want to put that in chat or your Q&A button, you can ask questions at the end. So I want to introduce the man himself, Jonathan Byrne. Are you there? Knock, knock.
Hi.
There he is. Awesome. You've got a presentation, so I'm not going to take too long. Just again, I want to let people know that this is being recorded. So if you want to watch it again or share it with your colleagues, please do so. You can find it on the HRAI YouTube page. And if you want to do a webinar of your own, I know summer's busy, but if you want to get up here, present on a thought leadership topic, we are more than happy to do something now. We're in the fall. You can find out more information under HRAI events or just by emailing us, and we'll get something sorted out. But with that, I'm going to turn off my camera, give it to the expert, and let you do your thing.
Thank you. Thank you very much. Hi, guys. So before we start, just want to introduce myself. My name is Jonathan Byrne. I'm from BITZER Canada. I've been with the company for just under 6 years, doing technical support and applications. So today we're going to be talking about controls and wiring for reciprocating compressors. So let's get started. So a bit of an overview of what I will be going over. So we're going to understand compressors and motor codes and what they mean. We're gonna go through some wiring diagrams, some electrical connections, production modules that we use to shut off compressors in the event of a problem, such as, for example, overheating of the motor windings, discharge temperature too high, or both. And then we're going to talk about some oil monitoring controls and finish it off with some sample wiring diagrams. So it's important to understand that when you have a compressor in front of you, it's important to understand the nomenclature, so that inside the nomenclature, you will often find your a motor code. Okay, and it's important to understand what that motor code means. So, for example, in front of you, you have an example of motor codes that we use here at BITZER for our semi-hermetic compressors. So the first digit that you'll find will mean the voltage that it's rated for. So 208, 230, 380 volts, three-phase, 60 hertz. 4, you'll be at 460. 5 will represent 575. Okay. Now, the second digit for in our motor codes, so you'll find D here is for star only, so direct online start. You have the E in this case here, but those are for single phase, and we're not going to talk about those today. But we use a capacity start, capacity run setup. But most compressors that you'll find are going to be 3-phase and not single phase. Anyways, then you'll have an N for 9-lead motor, and those are actually dual voltage. And then you'll find P for part wind. So you can actually do direct online or part wind. And then S here for direct online, meaning, but these are direct online starts only. And then to finish it off, you have the third digit here the U, and the U simply signifies UL. So here's an example of a schematic of what you would find on inside the terminal box for a small horsepower compressor. So you'll have your high voltage or your line loads, L1, L2, L3 will come and connect to your U, V, and W. Then you'll have over here, you'll have your thermal strip that is used for your low voltage. So to make it nice and tidy, you would connect your low voltage side on over here. Then you'll have your protection module, and the protection module is monitoring the PTCs sensors. Okay, and these PTC sensors are embedded in the motor windings. And by code, we're required to protect the branch circuit feeding the compressor. So on the nameplate, you'll find a stamp saying thermally protected or something of that nature. And what it means is that in the event that the motor is overamping, of course, it will get hot. And at some point, the protection module will take the compressor offline. For larger compressors, that temperature will be 212 degrees Fahrenheit that the motor is taken offline. Personally, I think that if you have consider this protection module as basic protection from the factory, but I think that it's a good idea if you were to put overloads in series with your contactors that would take the compressor offline sooner. And by having that dual protection will be a better way to protect the compressor. So here, and this is especially true for part wind motors, when you're with two contactors. So you have contactor 1 here, contactor 2 here, and these are used on all the conventional 4 cylinders, 6 cylinders, the larger 6 cylinders, and the 6 cylinders, and the larger octagon 4-cylinder recips. And they have a 50-50 ratio for the winding. So basically, you've got 2 windings, okay, doing the exact same thing. And in theory, you could wire L1, L2, and L3 onto this winding right here, but by convention and good practice, it's better to conform to the labeling on the compressor. So the first contactor here will energize 1, 2, and 3, and the second contactor will energize 7, 8, and 9. Okay, and you may think, well, wait a minute, 1, 2, 3, 7, 8, 9. Did somebody forget how to count? No. It's normal, and it's a convention that was adopted by NEMA. And when you have a dual voltage motor, you'll have 9 leads, and that's where you'll get your 1, 2, 3, 4, 5, 6, and then 7, 8, and 9. So by using the part wind start, it enables you to reduce the inrush by approximately 40%. And it's not the same for every motor, but it's just to give you an idea of how much you would reduce it by. Okay, and the overall starting torque is also reduced by approximately the same amount. However, when starting the starting torque of the first winding is set at 100%, so there's no reduction for the first winding. So what does part wine start does? It actually will reduce the strain on the electrical supply. So if there is benefits of doing that. Now, it might be a site requirement to use part wine start. Um, it might be, again, just to simply reduce the strain on the electrical supply. But is there a better way? Should I really go, direct online or part wine? It, it's up to you, or it's up to the constraints of what needs to be done, but there's pros and cons to both. So if you were to do direct online, you only have one contactor, it's less expensive, and it's easier for the control. But by doing that, you don't have the reduction of on the starting torque and on the starting current. Now, if you do part wine, it's a little bit more expensive. You have more parts, more chances of something going wrong. But you also you need to switch from that first set of windings to your second in 0.5 seconds. So there's also more risk. So again, there's pros and cons to both. But I just want to explain that there's no preference. It really depends on what the requirements are and what you want to do. So when you take the terminal box cover off, okay, you'll see on the inside of the cover a diagram that will be similar to the one that you have in front of you. And this is not intended to be a complete wiring diagram, but to be used as a great sample wiring diagram at a high level, where you will see, for example, you'll see your line loads coming in, hit a transformer, coming out, and then go to your safety circuit where you'll have your low pressure controls, high pressure controls, crankcase heater, an oil monitor, and then get tied into the protection module. Okay. And then the protection module then gets connected to the two male pins that you'll find inside the terminal box. Now, for the safety circuit, the wiring is the same for whether you do direct online or part one. That doesn't change. But where I want to bring your focus is, for example, on the left-hand side here, you have for direct online. So in this case, it's 575 volts. And what you would do is you would install bridge bars between pin 1 and 7, 2 and 8, and 3 and 9. And by wiring it this way, you now only have one set of contactors and you're wired for direct online start. Now, if I wanted to have my compressor wired for part wine start, I now have my first contactor, L1, L2, L3 going to my first contactor onto my first set of windings, 1, 2, and 3. And notice there's no jumper bars. Of course, you wouldn't have jumper bars in this case. And then from your second set of contactors, half a second later, you'll come and energize 7, 8, and 9. Okay. In the exact same rotation as you were connected on 1, 2, and 3. And I would recommend starting the compressor for each winding, doing a quick bump test, just to make sure that it's turning in the same direction. So for dual voltage motors, you have the motor code 2NU. You can either do 208, 230, 460, or 460 volts. So for part wine and direct online, you can have it wired for 208 or 460. It's not a problem. However, because it's a 2NU motor, what does that mean? Is that you actually have two 208, 230 volt motors. And this means that for a 460 volt configuration, you can only go across the line. And the jumper bars, what they do is you'll basically wire those two motors in series and run it as a 460-volt motor. So if you needed a part wind start setup with 460 volts, then a compressor, in our case, a 4PU motor code would be needed. You wouldn't be able to do it with a 2NU motor code compressor. Now, if you needed to do the part wind start for 208, 230 volts, you'll have to order a special terminal kit that will allow you to connect for the additional lugs. So similar sample wiring diagram as the single voltage one, but in this case, it'll be for the dual voltage. So for the safety chain side of things, exactly the same. But the difference here is that instead of 6 terminal pins, you now have 9. So like 1, 2, 3, 4, 5, 6, and then in the middle you'll have 7, 8, and 9. So by determining where you put your jumper bars, you can either run 230 volts direct online or 460 volts direct online. So by connecting 1 and 7, 2 and 8, 3 and 9, and then 4, 5, and 6 together, you'll be running 208, 230 volt configuration. And then for 460 volts across the line, by having your line loads connected to 1, 2, and 3, and have the jumper bars placed on 4 and 7, 5 and 8, and 6 and 9, you'll have those 208, 230 volts motors in series that will allow you to run 460. Now for part wind, the difference here for part wind start for the 2NU motor is you need to have a bridge bar installed on 4, 5, and 6. Then you'll have your first line voltage coming in on 1, 2, and 3. Half a second later, from your second contactor, you'll come and energize 7, 8, and 9. So here's a view of our 2NU 9-lead motor. This is what you would get if you took the terminal cover off. So you would have the protection module, you'll have your terminal plate right here, and then you would have your terminal kits for your jumper bars, your lugs, your nuts, and so on and so forth. But if you look at this right here, you have 1, 2, and 3. You may think, that's convenient. That's where I'm gonna connect. But if you do that, okay, you would run the risk of damaging the compressor. And what you need to do is you need to remove this black block so that you can have access to the to all 9 terminals so that you can put the jumper bars correctly as needed. With 7, 8, and 9 only energized, you would only have 50% of the motor that would be connected. And this is especially true for 460 volts because you haven't placed the jumper bars in place yet. So it's just something to think about, that not to forget to remove that black block so you can properly put all your jumper bars according to the wiring and the voltage configuration that you need. So here's a diagram just showing for direct online start. for 208, 230 volts, you have your jumper bars between 1 and 7, 2 and 8, 3 and 9, same as you would here. This is just to show you the internals. And then 4, 5, and 6, you would put the jumper bars there, which is represented right here. And it's just to show you physically what it would look like, and then electrically how it all gets tied in. Now for the 208, 230 volt part wind start, once you remove that black block over here, you see all your 9 leads. So you would put on your lugs, your jumper bars on 4, 5, and 6. Put back on your, and properly torqued, of course. Then you would put back on your black block, tight it down, and then you'll be able to put in your second from your second contactor. You come and power up, or energize, I should say, 7, 8, and 9. So just a note on contactors, you can easily have an undersized contactor, so it's important to understand how they're sized and what's the right size to get. So, for example, if we're looking for a contactor on a BITZER 4G23 5PU, this compressor would have a RLA value of 25.7 amps. And it would have a LRA value of 140 amps. And we add 25% to that value. So in this case, it'd be 175 amps. And the reason is to account for the inrush current. Now, wholesalers, they generally carry definite purpose contactors. And if you look at their ratings, in this case for a 30 amp FLA rating for 575, it would give you 120 amps. So if you were to only size it on the 30 amps being larger than your RLA value, you would end up with a undersized contactor. So it's really important that the RLA and the LRA values that you're sizing for will be met or will surpass. So the contactor needs to have an FLA rating that will be larger than the RLA value of the compressor, and its corresponding LRA value has to be larger than the compressor's LRA value with the 25% added. So the protection module that we use on our semi-hermetic reciprocating compressors is the SEB5, which conforms with the UL 60730. And what it does is that it will lock out the compressor in the event that the PTC sensors embedded in the windings are too high. It will take the compressor offline. If it senses an open circuit, it will take the compressor offline. And if it senses a short circuit, it will also take the compressor offline. And it will also protect against high discharge temperature. So the protection module, you would come and power up either 120 or 230 volts on L and N right here. Once this is powered, the two orange leads right here, Okay, this is where you will detect whether or not you have um, an open circuit. You'll detect a short circuit, or if the PTC's values are too high or not. So if everything is okay, then you're going to go from 11 and 12, which is closed, to open, and 11 to 14 will close. Now, right here between B1 and B2, you have a jumper that's in place. This jumper is in place to prevent automatic resets. And we strongly recommend to leave it in place, because if the protection module trips, you want to know. You don't want the same error to keep happening over and over and over again, because if it keeps happening over and over again, well, the problem is just going to become, it's going to get worse and worse and worse over time. So you want to attend to it as quickly as possible. So the PTC sensors, and what those are is they're positive temperature coefficients. And those are the sensors that we use in the motor windings. So for a 6-cylinder, for a 6-lead motor, you'll have 6 sensors. They'll be embedded in the windings, and its trip point is 212 degrees Fahrenheit. And for smaller 2-cylinder recips, it'll be 248 degrees Fahrenheit. So how it works is that you've got this resistance temperature curve. So as the temperature starts to increase, the resistance value starts to increase drastically. Now, when you're at approximately 8 degrees from your 212, you'll notice a rapid change in the resistance values. And this is to eliminate nuisance trips, and it's to get you more accurate readings. So once you hit your 4.5 kilo ohms, that will be your trip point on the protection module. And that's at that temperature that the protection module will take the compressor offline. To reset it, you simply remove power for 5 seconds to the protection module, and then you can reset it again. But if you did trip on motor PTCs, it could take a couple hours before the motor cools down and allows you to continue. Just something to think about. Now, the discharge temperature sensor. The discharge temperature sensor is a good thing to have when, for example, auxiliary cooling is needed, or if you risk running hot because of unloading, for example. It's an inexpensive sensor that you can add on to your system that will definitely give you great benefit. And how it is wired, it would be wired in series with the PTC sensors that are embedded in the sensor. Now, the discharge temperature sensor trip point is 284 degrees Fahrenheit or 140 degrees Celsius. Where does this sensor get to be installed? It's important to go back to the literature, whoever whoever the manufacturer is, and understand where exactly is the best place to install it. So in our case, we have 2 ports here that are designated for high pressure. And by looking at the literature, you'll see that position 2 would be used for the discharge gas temperature. And that would be the best place for it. So just a few notes on some wiring. So here's an oil monitoring switch. So we have OLCKs and OLCK1 and a delta P2. And these sensors are used, again, on our reciprocating, semi-hermetic reciprocating compressors, where you would use the OLCK1 on compressor models that would have a dynamic disk, meaning non-pump models, or the delta P2 for where you want to monitor oil pressure for compressors that have oil pumps. So these have 6 wires. So the first one would be your brown, and that would be your power. And this would be L1. Then you would have your blue, which would be your common or your L2. Then you would have your gray, which would be your single pole double throw switch. Then you would have your pink. And the pink is primarily used in the event that you have an alarm, if you want to send a signal or you want to have a light or something of that nature to indicate that you're in fault. That's what you would use that connection for. And then the orange would be the opposite side of your gray. It's where you would come out for your contact. It's a normally open contact that you would either wire to the compressor contactor or for the rest of your safety chain. And last but not least, your violet. Your violet is what tells the oil monitor that your compressor is now, it has a run signal. So you can start the 90-second time delay before starting so that it gives time to the compressor pressure to stabilize and for the foaming to reduce so that you can get either a good oil or a good oil pressure. And this would be wired to an auxiliary contact on the this would be wired to a normally open auxiliary contact on the compressor. So here's a sample wiring diagram with all the controls. So you have your control box here. You have your contactor. You have your compressor contactors. You have your motor terminal, your terminal plate for your compressor, where your 2 orange leads from your protection module would come and monitor the PTCs embedded in the motor windings. You would have your oil monitor, whether it's your OLCK1 or a delta P2. And then you would have your control, so your low pressure, high pressure, and then your violet wire that's wired to your auxiliary contact, normally open auxiliary contact of the compressor. Now, we have seen that on some sites, especially people that wire the delta P2 with 2 lines of 120, that you're getting a voltage ghost. You're getting the violet wire is being energized when the compressor's not running yet. So this is the new preferred wiring schematic for the delta P2 or the OLCK1. So you would wire your violet and your orange together going to your compressor contactor. And that is now the new way that we're wiring those to eliminate for those nuisance trips. Now, when we before you're doing a startup, or it's important to make sure that inside the terminal box that you have the correct voltage for the application. You have the terminal box is clear of any debris, that all your lugs are properly torqued, all your bolts, your nuts, sorry, are properly torqued as well. Jumper bars are properly placed depending on what configuration you're trying to achieve. Now, when we're looking for problems, we're not sure if the motor is burnt or has lost a phase or what have you. What you can do is you would strip the 6 leads from all the bolts, the washers, the jumper bars, so you have the bare naked pins. And what you would do is you would read the resistance between pin 1 to pin 2, pin 2 to pin 3, and then pin 3 to pin 1. And then the same thing for these pins right here. So 7 to 8, 8 to 9, and then 9 to 7. It doesn't necessarily matter what the resistance value is, as long as they're all the same. Okay. Now, if you were to use a megger to test your values, you would never want to use it with higher than 1,000 volts, and I would actually recommend 500 volts if you were to use it. But generally, this is not necessary, because these compressors are already tested at the factory, and when they are tested without oil. Now, doing this test with the megger at 1,000 volts with oil, the oil will actually conduct and can damage the motor. So you got to be careful with that. On a 2NU motor, to test the resistance between the terminals, what you would do is you would test between pin 1 to pin 4, pin 2 to pin 5, and pin 3 to pin 6. And again, with all the jumper bars and nuts and lugs removed. And then you would do the second set of readings between 7 to 8, 8 to 9, and 9 to 7. And these values between 7, 8, and 9 will be twice the values that you would have got on your first readings. Now, this is just an image just to show you overheated connections. It can cause refrigerant losses. It can damage the compressor. So it's really important to make sure that when you have your connections on L1, L2, and L3, that they're properly terminated, that they're properly torqued, that you haven't you didn't reduce any of the when you clamp them together to the lugs, that you have a good connection, that the insulation's not pinched, because otherwise you can end up with problems. So PTC sensors for that are embedded in the motor windings. So for a 4PU, 5PU, 2NU, you'll have 6 sensors, and they're approximately 50 ohms each. So with all of them in series, you'll have a reading of 300 ohms in total. Okay. The discharge temperature sensor will be less than 100 ohms. And when you connect it in the PTC loop, it'll generally be less than 500 ohms would be the reading that you would get in total. Again, the protection module, the trip point is 4.5 kilo ohms, and the will reset at 2.75 kilo ohms. And it may take a few hours for the windings to cool down before you can restart the compressor. To reset the module again, simply remove power between L and N for at least 5 seconds. Now, what to do if you have a line side or a low side imbalance? What you can do is by measuring, by putting your power line on over here with your motor load, power line 2 with your motor load 2, power line 3 with your motor line 3, you would take down the amperage readings that you would get. You would calculate the average. So in this case, it's 30 amps. And the max deviation that you see here is between power line 3 and motor lead 3, which would be 6 amps is the difference, is the biggest deviation between your average and what you read. So then by maintaining the same rotation, what you would do is you would keep motor your motor lead 1, 2, and 3. You wouldn't change those, but what you would do is you would take your power line 1, move it here, and then power line 2, move it down here, and power line 3, you would move it up here. And then again, you would take down your readings that you would get, calculate your average, and determine what's your max deviation. So in this case, it's power line 3, motor lead 1. 31 amps minus 25 amps gives you 6 amps. So again, it's the same one, same issue. You would repeat the test again a third time. This time, your power line 1 that was here, you would move it onto here. Your power line 2 that was here, you move it up here. And then your power line 3, you would move it down here. You determine your values, your amperage readings that you're getting, calculate your average, and then determine your max deviation. And then when you look at the results between all three, is it a line side or a low side imbalance? As you can see here, it is a power line imbalance that you have. So that concludes my presentation on wiring and controls for semi-hermetic reciprocating compressors. I hope you have all enjoyed it. And if you have any questions, please let me know.
Well, we certainly have questions, so I hope you're ready for them, Jonathan.
Okay.
From Henry, you mentioned that for many applications, DOL or PW is a matter of preference. However, I would like to know which of the two methods is more common for refrigeration applications in Canada. And before I throw that to you, I'm just going to allow Phil Boudreau, who many of the people on this call are familiar with from BITZER. Phil, I've enabled your mic. Are you there?
I'm here.
All right. Good to, well, not see you, but good to hear from you again, Phil.
Yeah, actually, yeah, I'm not sure what's up with the camera thing here.
No worries.
That's okay. Nothing to see here.
Happy to hear you. So I'll pose this to the both of you. So from Henry again, and I'll start again. You mentioned that for many applications, DOL or PW is a matter of preference. However, I would like to know which of the two methods is more common for refrigeration applications in Canada.
I think I did say it's a matter of preference, but it could also be a requirement for a certain particular site. Which one is more common? They're both equally used. It's really up to the contractor who's installing it. If there's no requirement if there's no requirement on the site, I think it's really a preference for the contractor.
Yeah, and there's a couple of things that drive this as well. Depending on the voltage, the lower the voltage, if you're into a 208, 230 volt supply, the motor wiring, the electrical wiring, of course, gets somewhat larger. The amperage is larger, or higher. So sometimes, end clients may decide to go part wind start just to reduce the impact, the inrush on startup and that sort of thing. And certainly costs of switchgear, wiring, everything else. Aside from that, I would, in 575 volt up to approximately 50 horse, I would say it's more common to see the direct online start approach. And when you get into larger motors above that, now you're really getting into screw compressor territory where the part wind start becomes a little more common. And then of course, aside from the part wind start and the across the line start, there's also soft starting and VFD, which are two other options used as well.
Thank you. Another one from Henry. Are any of the PTC sensors on BITZER compressors replaceable?
Not the ones that are embedded in the motor windings. They are not replaceable. Because you would have to remove the you would have to remove the motor, and these are press fit motors. So no, they're not cannot be done out in the field.
We got one from Chris Wright. Hello. When troubleshooting electrically from a terminal to the ground, should there ever be any continuity to the ground? Any resistance value to the ground normal, or is OL expected?
OL is expected. If you have a low reading, or if you have a low resistance or something like that, then it's bad. You've lost a phase.
Great. Phil, I saw your mic go flash there for a second. Anything to add?
Oh, sorry, that was not intentional.
Oh, no worries. Okay. We got another question here. Can we connect compressors by across the line?
Yes. So direct online or across the line, they mean the same thing.
Okay, thank you. Last question here. If you want to get in your question, now's the time to do so. From Henry again, is the SCBS module being replaced by the newer version of CMRC?
So to answer this question, starting January 1st, 2025, the CMRC 02 will be replacing the SCB modules that we have in our terminal boxes.
All right, there we go. Rapid fire question answer session. I think you did pretty well. Now you've got your contact information up there. If people want more information, this video is also going to be on HRAI's YouTube as well. If people want to go back and look at it, any parting words before we go? I do have one more question.
Yes.
All right. And this one, late entry. For contractor sizing, I see you use 1.25x LRA factor. We usually size contractors by max HP rating of the contractor and the actual LRA of the compressor. Is the 1.25 factor only for DP contactors? And I was saying contractors, but I meant contactors.
Contactors.
Just misreading that. Yep.
Well, the 1.25 is really to account for the inrush. So that you have a contactor that's not undersized. But the way that I had it laid out for the FLA times 4 for example for the 575, that is how that's how it is determined, those ratings for definite purpose contactors. For other contactors, they're determined another way, but at the end of the day, what you really need to do is you need to make sure that the contactors FLA and LRA values will be larger. Both of them will be larger than your RLA of the compressor and the LRA of the compressor, meaning your locked rotor amperage and your rated load amperage. So as long as those two values are higher, you'll be good to go.
And just if you don't mind me chiming in here, Jonathan.
Oh, please do.
Just another note on these the definite purpose contactors. Every definite purpose contactor in a 575 volt rating, 575 volt voltage, has a locked rotor amperage carrying capability that is exactly 4 times that of the FLA of the contactor. Okay, with 460 volt, it's 5 times, and with 208 230 volt, it's 6 times. So if you're sizing a contactor based on just the RLA, you're probably going to run into issues with an undersized contactor with 575 volt, because the multiplier is only 4 from full load amps up to locked rotor amperage. So this is why we talk about both the full load amperage of the contactor comparing with the RLA of the compressor. Having some safety buffer in terms of the sizing is of course always preferred. And then the LRA of the compressor should always, or of the contactor rather, should always be greater than the compressor. You know, we're talking about a compressor that's worth a significant amount of money compared to the contactor. So in our view, it never makes sense to just size contactors right on a line like that. Give yourself some buffer there, because that is kind of a weak link, or can be. So play it safe and use the larger contactor.
And since we're talking about contactors, when replacing a compressor, it's a really good idea to replace the contactor as well, because it'd be a shame to replace the compressor and lose this new compressor because of a bad contactor. So for the little money that it costs for the contactor, change them both when you're doing a replacement.
All right. Thank you very much to the both of you, Phil, Jonathan. A lot of good stuff. If you have any more information, you can reach out there. But until then, we will see you all next time.
Thank you very much.
Thank you so much. And thanks for everyone for showing up. Cheers.
Thank you, Matthew.
Thank you, Matthew.
Our
Bye-bye.
pleasure.